Fine, so here we're going on to the second part. These are the longer questions. So we have simple harmonic motion and the greenhouse effect. We're not going to be looking at that. A body is displaced from equilibrium. State two conditions necessary for a body to execute simple harmonic motion. Now, this is your basic defining formula. So you can say the acceleration or the force, one of the two. The acceleration, I'm going to say the acceleration is proportional to the displacement from the equilibrium. Remember, we're always from the equilibrium, and the acceleration is always in the direction towards the equilibrium. So as it goes to and fro, so if this particle is, for instance, oscillating like that, and that's x0 minus x0, then if it's over there, if the particle is over there, that will be your displacement x. Your acceleration will always be in the opposite direction for that displacement. So if the displacement is there, it's x. Your acceleration is always in the opposite direction, always towards your equilibrium point, and it's always proportional to that value. Okay, that's the basic fundamental definition of simple harmonic motion. Okay, so going down to this next question here. Let me just bring that a little bit further up. Okay, so in a simple model of a methane molecule, now you don't really need to know what a methane molecule is, but it just explains that here a hydrogen atom and a carbon atom can be regarded as two masses attached by a spring. A hydrogen atom is much less massive than a carbon atom, such that any displacement of the carbon atom can be ignored. So we're just imagining basically a situation like this, where you've got a spring and it's been attached to a hydrogen atom, and this atom is vibrating to and fro. The graph below shows the variation with time of the displacement x from the equilibrium position of the hydrogen atom in a molecule of methane. Now, you just got to be really careful here. Let's just look at your graph. Firstly, this is this basic cosine graph we've got here. We've got your cosine graph, which we know. You need to watch these multipliers. This is 10 to the minus 10 and 10 to the minus 13. So don't forget those when we are working out our problems, or when you're working out the problems. You also get told that the mass of the hydrogen atom is 1.7 times 10 to the minus 27 kilograms. Okay, so we need to use the graph. So we've got to work from our graph. All the information should be there. Let me just clean up the graph a bit. Okay, so to determine the amplitude. Now the amplitude is basically our x0. It's going to be this 1.5. It's this highest point over here. So it's going to be 1.5, but don't forget your multiply, times 10 to the minus 10 meters. So that would be your answer to that. Show that the frequency of oscillation is 9.1 times 10 to the 13 hertz. Now from the graph we can actually get what we call the period. We can get the period of the graph, and that is the time taken for one complete oscillation. So we have that, and the period, the t, for this graph. Now you've got to look carefully at your units, at these over here, and see what does one little block mean. So we've got here that it is each of these, two of these little blocks is actually going to equal 0.01. So we have that over there. So we've got here about, it's going to be about 1.1, if I'm reading it correctly, times, and here we've got to be careful here, times 10 to the minus 13, sorry, minus 12. Alright, well so it's 10 to the minus 13 seconds. Alright, so we've got 1.1 times 10 to the minus 13 seconds, and your frequency is equal to 1 over t, would equal 1 over that value there, and you should get a value of about 9.1 times 10 to the 13. Sorry, let me just check out something here. This is not 1.1, but it's 0.1. Don't know why I'm saying that. Alright, so it's 0.11. That's what I've got there. 0.11 times 10 to the minus 13. And so when we put that over that, we should get that. And this obviously is in seconds to the minus 1, or we use the symbol of hertz. Now, we want to show the maximum kinetic energy. Now, we've already used this. From here, we see that our T frequency is equal to 1 over T. So we want to find the maximum kinetic energy. We've got this formula is our maximum kinetic energy, and when looking at it, we've got everything. We've been given our mass. We've worked out our x0 from the graph, but we don't know what the omega is. But we can use this formula to do that, because omega is equal to 2 pi over T, but from this formula over here, we can say it's equal to 2 pi f. So if I put that in, I can work out my omega is equal to 2 pi f, and I should get something like equals 5.7 times 10 to the 14, and that's going to be radians per second. Radians per second. And then I put it into my formula EK. Let me just work over here. EK max is equal to a half. We got that over there, the half, times the mass. So the mass over that is this over here, 1.7 times 10 to the negative 27, times our omega squared. We're going to have omega squared, so we're going to have that squared. I'm just going to write it, and I'm sure you can do the calculation here, times by our x0 squared. So it's this one over here, our x0 squared. And from that, you should be getting something like 6.2 times 10 to the negative 18 joules. Now, just a point on significant figures. See here, if I look at this, I need to put these in as two significant figures. All our values here on our graph are two significant figures, so we would make that our most accurate answer. Okay, so going down to the next part over here, it says on the grid below, sketch a graph to show the variation with time t of the speed v of the hydrogen atom for one period of oscillation at t is equal to 0. Now, we had that our graph was for the displacement was the cosine graph. So from this over here, we're going to have our velocity will be minus the sine graph. We got this v0 value. They say here that there is no need to add values for the speed axis. So we can choose that. We can choose our values as we like for that. But we're going to go minus. Now, in looking at my displacement graph, I can see that I get it will start off over here, obviously, and it will go down, and you would be at your quarter of a cycle. Well, it's you'd go down. It would go down like, and you'll get your quarter of your cycle after it's at this point over here. So if you check your graph, it's not very well synchronized. You're going to get your, sorry, not there. It's a little bit further. This side, you're going to get a quarter of your cycle is going to be over here. There. You get half a cycle over there, about over there. You get 3/4 of a cycle coming back over here, where it goes through that. We're looking at about there. I must make sure that I've got the same amount on either side, and we come back to here. So you're going to get something like this. And that would give you your velocity. It goes in a negative sign graph like that. Then it says, to continue with that, it says the next question there, assuming the motion of the hydrogen atom is simple harmonic, its frequency of oscillation of F is given by the expression, this expression over here, where K is the force per unit displacement between the hydrogen atom and the carbon atom, and MP is the mass of the proton. Show the value of K is approximately equal to that. So we have our value for frequency. We've already determined that. So I can just change this formula around. This is going to be F squared 4 pi squared is going to equal, and then we're going to take the square of that, and that's going to be times MP will equal K. And then I can just substitute that in, all my values into that. We've got our frequency, we've got that before. We were given the mass of the proton, the mass of the hydrogen atom is that, and from that we can work out our K. And we should get something like 560 Newton meters. Alright, and then going down here, where it says over here, estimate using your answer in D1 the maximum acceleration of the hydrogen atom. Now from this we know that our acceleration is equal to minus omega squared x, like that, and we can use because our force is equal to, because we know that our force is equal to ma, and it's also equal to, if we think of Hooke's law, it's equal to kx. From that we can see that acceleration is equal to k over mx, like that. So this k over m would correspond, the square root of that would correspond to your omega. So if we take our this k, we've worked out this k, it's 560. So our acceleration is going to be the 560 divided by our mass, which is equal to 1.7 times 10 to the negative 27, and then times by this x over here. You're going to get your maximum acceleration, because they wanted your maximum acceleration. Because they want maximum acceleration, that is at x0. So you're going to put in your x0 value, which is 1.5 times 10 to the negative 10. And when you calculate that out, you should get about 5.0 times 10 to the 19 meters per second to the minus 2. So you're getting huge accelerations that are taking place.